Given that on Earth, g is equal to 9.81 meters per second squared, ignoring air resistance, how far will an object released from rest have fallen after 1 second, 2 seconds, 3 seconds? And it's telling us to ignore significant figure rules on this one, so I think we'll be happy to do that, hopefully. The formula we're looking at here is the free fall formula, the one that Galileo discovered, and that we've been looking at a little bit already. D is equal to 1/2 gt squared. So really, I think what I'm being asked here is to calculate distances for t is equal to 1 second, 2 seconds, and 3 seconds. So for t is equal to 1 second, that would imply a distance d is equal to of 1/2 times 9.81 meters per second squared times 1 second. And if I put that into my calculator, I'm really just going to do 1/2 times 9.81 times 1. I don't even need that 1 really, because that's not going to change anything. And so looking at my calculator for a little bit of help here, I get the number of 4.905. What about the units? Let me see. Oh, I think I screwed something up. This may be a good point that sometimes I screw things up here. Should this have just been 1 second? This was t squared, right? This should have been 1 second squared. Doesn't change the number, but it does affect the units. So it's always important to check units in physics. So meters per second squared times 1 second, but then squared, that's a second squared there, cancels that one. So I'm going to get meters, which is really sensible and what I expected given the fact that I'm calculating a distance. Let's look at the other two. I've got for t is equal to 2 seconds. For that one, we're going to say d is equal to 1/2 times 9.81 meters per second squared. This time times 2 seconds squared, which is really going to be like 1/2 times 9.81 times 4, right? And getting some help from my calculator, I get a number for that of 19.62. And again, the units should be meters. And then for 3 seconds, kind of same thing here. 1/2 times 9.81 meters per second squared times this time 3 seconds squared. So we can definitely see distances like proportionate to time squared and how that kind of scales here. These distances are getting quite a bit bigger as time goes on. Maybe something worth saying here, though, is like this. We've been ignoring air resistance. So this is an issue I've sometimes seen come up with this is like if you Google stuff or look at online materials, things like terminal velocity will come up. Those are concepts. That's an example of a concept associated with if there is air resistance as something, since it's really traversing much larger and larger distances following the pattern of this d is equal to 1/2 gt squared formula, that means air resistance is going to increase if it keeps doing that. And in reality, in that sense, you can't just ignore air resistance forever. You might be able to do that if it's a small drop and you're only looking at a few seconds, but given enough time, air resistance will start to matter. And at some point, air resistance will actually become strong enough to kind of counteract the weight force, we'll find out, that is pulling this thing down, and it will no longer continue to speed up. And at that point, it will be gaining in distance at a constant rate. So that's just something to be aware of, that's out there. So in physics, in this class, oftentimes I'm going to be saying ignoring air resistance, and sometimes I might forget, and you should just assume that that is the case. But anyways, I think we can go ahead and check these numbers here and see that we got everything correct.